Now we will look at the deduction function in more detail. So what a theory deduction does is that looks at the atoms assigned so far and checks the following. If the current atoms are currently unsatisfiable, then it gives you contradiction response, and if not, then it sees that if are there other literals in input formula G that are implied by the current assignment. This is the thing which we have not seen this before, and please try to understand this additional power that a theory deduction precision can give you. Any implementation must comply with the following codes. Correctness means that the Boolean model is consistent with T. If the procedure terminates and theory deduction says, oh, all good, then the Boolean model must be consistent with the theory T. The termination. So the partial model should never be repeated. The return conflict clause by the theory deduction should be powerful enough such that the same partial models are not tried again. So what is the interface of a theory deduction function? It takes a conjunction of atoms, the current Boolean model, and the decision level and decision stack. And it returns a clause of the following form. So please notice that L is a set of literals, okay, that are assigned inside the model M. And L is a subset. Let's suppose you have a x greater than or equal to 2 assigned to true, or x equals to 0 assigned to false. L may be saying is that is a conjunction of x greater than or equal to 2, negation of this, and x equals to 0. Something of that sort. Conjunction of literal implied by another literal. This literal L can either be one of those elements that appear in input formula, or it can be false. So what a theory deduction can respond to you that the conjunction of your literals that are already true imply this another literal L that appears in the formula, or it can tell you that the literals already you have implies false. For example, you have a theory deduction call with this following parameter where you have two atoms, and you can easily see these atoms are mutually contradictory. So, and if you are using a theory deduction for quantifier free linear rational arithmetic, then it will respond to you with by this returning this clause. It says that if these two atoms are true at the same time, that means false. You can easily see that this is a clause because these two are inside the left hand side of the implication. So if you just simplify, try to simplify, it will become or, this adds not, this is an or, and again this is put a not in front. Again, another example, if you have this these two atoms being passed, then what you do, you can also return this kind of clauses. You can see that these two atoms together are not unsatisfiable. They can satisfy them. However, let's suppose atom x plus y greater than 0 appears in your formula, then you can return this clause. You can say that if these two are true implies this atom. The output of a theory deduction must satisfy the following conditions. Okay, so let's look at what the spec. We saw the very high level spec, it's correctness and termination property. Let's see what do we want. If the input is unsat in theory T, then CS, the set of return clauses, must contain a clause with the right hand side literal is false, and which says that these are the set of inputs, set of atoms which are mutually contradictory, and please never assign them together again. And at the decision level, as usual in the CDCL, what decision level you should undo such that this exact contradictory set of assignment is undone. Let's suppose your input set of atoms are mutually satisfiable, then what you do, you return same decision level, and it indicates to the high level algorithm that that no change is needed. The current assignments are consistent. It may give you extra information. Clauses coming in this situation will tell you that the current decision can imply these additional literals that may appear in your formula. Let's look at an example. This is an example for overall CDCL algorithm. Consider f prime. It has three clauses. This clause, and first done the Boolean encoding. What is the Boolean encoding? You have x1 here, x2 here, and this is a negation of this literal. So you say x2 not of x2 here, 3 is there, and x4 is there. So we run a CDCL, and in CDCL you do unit propagation, then x4 gets assigned to true, and then you, since there is nothing more to propagate, you make another decision. You set x2 to false. Then you do unit propagation. Now what has happened? This literal has become 0. Then this literal has to be made 1. So therefore unit propagation set it to 1. Once you do that, you have this literal has become 1. So this clause is satisfied. This clause is satisfied. This clause is satisfied. All clauses satisfied. So now what you can do? You can call theory deduction. You can see, okay, I have assigned these literals to be true, and ask the theory, is it satisfying or not? If you do that, you can see that x equals to y is not equals to z, and then I am saying z equals to x, which cannot be possible. We will get a contradiction. It will return the clause looks like this, which will say that one of them thing must be true. And you apply Boolean encoding on this clause, and then you obtain a clause which win in terms of Boolean variables, not of x1 or x2 or not of x4. Now I add this clause to my set of clauses and do the unit propagation. If I do that, my x4 becomes equals to 1, x2 becomes to 0, and x1 equals to 1. And this conflict with the learn clauses. So I will do the backtracking and make some other assignment and move forward. So how do we implement this theory of propagation? So usually it gets implemented using theory solvers. We will call them DP. For a given theory, you need to have a decision procedure. And let's suppose this is available to us. So what it does, it takes input constraints as a sequence of literals and maintains a data structure that defines the solver state and satisfiability of constraints seen so far. And it must provide the following interface. I mean, this interface is not universal, but this interface is conveniently fit with what we need to implement our theory deduction function. So you should be able to push. If I give you a literal, you should be able to add this literal in your constraint store of the theory solver. You should be able to remove by pop. It removes one element from the pop store. Checks that. It checks the satisfiability of the current store. And unsat code. This is a new idea. What it does is that it looks at the current set of literals in the store and say these three things are mutually unsatisfiable. If all these three are present, then certainly your formula is unsatisfiable. And this function tries to find the smallest set of literals that you can clearly say that they must not be true at the same time. Now let us see how can we implement theory deduction using decision procedure for some given theory. The theory deduction, we have seen that takes a set of literals as input, and then also reads a partial model and the decision stack, decision level, and the formula which is input formula. So what it does, it first pushes each literal of ls in your DPT, and once it pushes all of them in, it can query is it set is if it is unsatisfiable, then it goes here and try to get the unsat code. Unsat code is a subset of ls, and such that you get these literal, we know that they cannot be made true at the same time, and at least one of them should be made false in the future assignments at the Boolean level. However, if our unsat code returned whole of ls instead of giving a subset, it's fine. It will be correct answer, but it will be inefficient. Smaller the set is, it's a better outcome. Then what we do in a very complicated mathematical term, we are saying the latest decision level which participates in an unsat code. If a literal appears in that unsat code and that literal was decided after certain decision, that's one of the decision levels you need to worry about, and you cannot go behind them. So the maximum decision level that gets involved in the unsat code. Then what do? We return the negation of conjunction of these literals, and that is becomes, this is a clause and this is a decision level. On the other hand, if we have a satisfiability, then what we can do, we can collect implied clauses. What are the implied clauses? If some subset of our ls, let's say ls prime, implies some literal L, then we can add this thing as a clause. So that's process is here. What we do, we for every literal that appears in our formula G, we add the negation of that literal in our decision procedure. And then what we do, we check if it's unsatisfiable. If this is unsatisfiable, that means that the ls implies L. Now we collect the unsat code and we get ls prime, and again we add this ls prime in our set of the return clauses. Note that now I'm not changing my decision level, so original decision level remains the same, and we don't change it, and we return the same decision level as we received. However, we keep adding these clauses which somehow encode that the current decision implied L. If you carefully analyze this algorithm, you will find that it is guaranteed that ls prime contains not L. And then finally, when we collect all the implied clauses with respect to all the literals, we return the set of collected implied clauses.